শুনতে পাচ্ছ?
হ্যাঁ স্যার।
ঠিক আছে, ঠিক আছে। Sure. All right. So let me just, since we had a long break and where we were, let me just try and spend 5 minutes to get you back into it. We did some stuff on lattice, and then we made a transition from or were in the process of making a transition from lattice to continuum. And the technique was that when it was a lattice, then I was using the whole business of StatMech, calculate partition functions, and it was minus beta EI summed over all the site psi. So for some configuration, that this is sorry, not sites, but configurations, some configuration having the energy EI and sum over all configurations I. So that's the partition function. And so now this is a discrete, what we have been doing is a discrete sum over the label I, and we wanted to make a transition to a continuum description where we talk about this region here, and that region around a spatial point, a small region around a spatial point R. This region has volume D3R. In this volume D3R, there are a number of what is this? So inside this D3R, the configurations that one has to take into account. So this sum over here is now going to be in this D3R. There are a set of configurations, and I would have to replace local quantities, which is the number of configurations over here, and it is, let's say, G of R e to the power minus beta e at locally at R, and this is and then there is D3R. So this is the local, and then there is an integral. This is going to be the total energy over here, which you are that's the sum over it's a total energy for a given configuration. So for a given E of R, I would have to integrate over all space and get integral E of R. So the different configurations are now different expressions for E of R. There is one functional dependence which corresponds to one configuration. Another configuration is a different E of R, and you are going to do a sum over all the essentially all the different configurations. And now the point is that this G of R, which is the number of configurations corresponding to this energy E of R over here, that is going to be like so it is S equal to K log gamma. So that is the number, gamma corresponds to this. So it goes up into the numerator. So this goes up to D3R. There is going to be e to the power, and there is now beta, and there is going to be t, so 1 over kt, so there is a t, and there is the entropy, which is the S of R over here. So it is, and then you would have to integrate out over all R here. And then there is the e to the power minus beta, and there is this e of r d3r over here. And therefore, what you are looking at over in this numerator is the beta free energy e minus ts f of r d3r integral. So from this, sum over all configurations of e to the power minus beta ei, I have come to this part over here, which is e to the power minus beta integral f r d3r. If it's a d-dimensional space, it would be d of dr. So from here, this is the configuration, a particular configuration, meaning that I have to give you the energy at whatever it's the ith configuration. Ith configuration energy in this thing, which has gone to the continuum over here, replaced by this for a given function f of r. So a given configuration over here to a given function over here, sum over all configurations over here has to be a sum over all integral over all configurations over here. So integral meaning essentially integration over all possible. This is integration over all possible forms of f of r. So all right, so that is what we were supposed to do, and now to do that I actually need a model. So I need a model for doing that, and just as to calculate this one over there, this I needed E. So E, for example, Ising model was minus J summation Si plus 1. So E was this, EI is simply this, and then the total E, which is a sum of, is this quantity over here. So EI is this bit, and then it's the total energy which corresponds to this integral over here. So it is, and for all configurations S, the configurations are determined by what we are saying. For example, the Ising is Si at any site I. Si can be up or down. So that is the thing which we had been doing, which is now transferred to this over here. So if I want to make any progress, then I have to now talk about what kind of a form is f of r going to take. So what you say, we are in the business of doing talking about critical phenomena. So critical phenomena, the phenomenology is, that there is something like a magnetization or a density which we have given a general name, order parameter. And the characteristic of the order parameter is that it is its expectation value, the mean value is 0, t greater than tc, and non-zero for t less than tc. So that defines the critical temperature, the critical point. So this is what we have been doing for the first couple of days, that There is, I mean, van der Waals equation had a density difference between the liquid and gas phase. Magnet had magnetization, which can be zero or non-zero. So it is an order parameter, which is like a magnetization. And so the quote unquote magnetization, it is, I mean, magnetization takes into account the van der Waals also. Instead of calling it a density difference, you just call it a magnetization. So this word magnetization used, which we will be using, is a loose word, meaning that essentially we are talking about something which has zero expectation value above TC and non-zero expectation value below TC. So that is what the order parameter is all about. And the free energy is to be expressed in terms of the order parameter. And now the point is, you see, that you can make an expansion, because the free, at t equal to Tc, it is T above, it is going to be small. So very close to Tc, this order parameter, whether it is the magnetization or whether it is the, so the expectation value is small. Fluctuations around the expectation value are not, the expectation value is zero above Tc and small below Tc. And there were the fluctuations about the expectation value, which is what we are going to be concerned with. And it is the phi of r, which is the order parameter variable, order parameter field. So this order parameter field has a zero expectation value equal to 0 for t greater than Tc and non-zero for t less than Tc. I can, because of this, I can do an expansion. If all this is good for whatever we write down and do for the next few days, is all valid in the vicinity of Tc. Say T minus Tc over Tc, this quantity in magnitude is 10 to the power, let's say, -2 or smaller. That essentially is what, that is how small a region you are looking at. And that is where we will be, that is the region which we will be concentrating on. So it, in some sense, it's extremely specialized, that you are, if I'm looking at a magnet, the magnet has a magnetization at all temperatures, but my interest is only in the magnetization which is near the transition, where it goes from zero spontaneous magnetization to non-zero, and in that region, just over the region where this transition from zero expectation value 0 to non-zero is taking place. That allows me to think of an expansion. So this phi of r is the local magnetization, and you write the f of r as an expansion a phi squared by 2. So you start with, I mean, it is going to be whether you are going to write, sorry, f of phi. This now is this f over here. I mean, it is f of r through the function phi. So phi is a function of r, and f itself is a function of, and that is how, I mean, the f of r comes about. So it is a times phi squared. It is going to be symmetric, with it does not depend on the sign of phi. So it has the energy is independent of, the free energy is independent of whether phi is positive or negative. So it is a symmetric function, and then phi is a function, therefore there will be gradients. And the gradient is this grad phi square. And then you need to have the next order terms, lambda over 4, phi square squared. I mean, the phi squared is in general phi 1 square plus phi 2 square up to phi n square. If it is like a Ising or like fluids, then there is only phi 1. Phi is one-dimensional, and there is only phi 1. And phi is good. But if it is a standard magnet, I mean the Heisenberg magnet as it is called, so if it is a standard magnet, the magnetization vector can point in any which direction, then phi is a standard vector with components phi 1, phi 2 and phi 3, and phi square is equal to phi 1 square plus phi 2 square plus phi 3 square. If phi happens to be a planar magnet, that is the magnetization is forced to lie on a plane, then phi is a two-dimensional vector and it is phi 1 square plus phi 2 square. So phi in general is n component vector. And the action goes on in a d-dimensional space. So this is the dimensionality of space over here, and f is functional, which means a function of a function. Phi of r is the function, which is the magnetization variable, which is a function, different values at different points of space. And the f is related to the f is written down as a functional of this phi over here, which is this, and then integrated over dr. It depends only on phi. So f over this, what you have over here, is a functional which depends only on phi. So function of a function, this quantity over here is a function of f alone, and that is, you give me a f, I give you a number. You give me a phi of r, you give me a function, and I give you a number. So function to a number. Normally it is number to a number in a function, in a functional function to a number. So all right, so that's that. So so that is the setup. The setup is then, which is what we had arrived, that if instead of a discrete system, I'm going to talk about a continuum, then my starting point is this f of phi, and I have not written, I mean, there is no, at this point, I have no reason to terminate this. I should be having another term. I could be having phi square cubed, and I could also be having del square phi whole square. So why would there be a question about phi square cubed? What happened to these terms over here? Why did I not write them down? I write down only up to this point over here, and we will hopefully in the course of the day today give you some idea why this is justifiable. So this is so what does the problem reduce to? The problem reduces to the calculation of this partition function, which is a functional integral, which means I have to integrate over all functions phi, and then over here is e to the power minus f in general ddr, And so this is the general structure. Let me just write 3 for now, but whatever I do is going to be true, whether it is 3 or 2, or you just simply have to make the appropriate changes at the as you will see. So d of phi of r e to the power minus f d3r, and that is the integral, which is where we certainly had arrived last time. That gives you the partition function. Thereafter, if you know partition function, all the other thermodynamic quantities follow, which you know very well. So all right, so it is a question of this partition. But now that means that I have to carry out this integral. So if I stop at this point over here, phi square grad phi square square, then the functional is called a Ginzburg-Landau functional, and is obviously the that is vital. That is essentially a most important part of the literature in some sense, and so everybody focuses on this. But right now you don't know why, but we'll get there at some point, hopefully today. So Ginzburg-Landau functional, that is what this is, this f of phi. I mean, when put over here and integrated out, what you get is a Ginzburg-Landau function. And now I have to do this integral, which is overall. But that is where we were last time also, that as told you that we can't do only in functional integral that I can do in this world is integral I, which is equal to d phi and e to the power minus a phi square. So let's say by 2. So that's the only one. Now this is no different as from this term over here, for the reason that d3r, because the way we did it, we had to have a meaning. See, the most important part of it is that I need to have a meaning for what is meant by all functions phi. So for that I went to the Fourier transform, which was defined as the phi of r is equal to integral d3k. I mean, normally it would be a ddk, and it would be 2 pi to the power d over here, and then it is ek I k dot phi of k. If it is a vector, then I mean there would be say vector phi, then for each component there would be a relation of this kind. So I mean in general, if it is the alpha component over here, it would be the alpha component over here. So I have this, and as soon as I have that, what I showed you last time is that this chap over here, integral phi square d3r, goes to integral phi k phi minus k d3k over 2 pi cubed. So that is what phi squared becomes. So phi squared d3r is this, and that's just taking the Fourier transform, putting this in, doing the integral, getting the delta function defined, and you are down over there. So 2 integrals over k1, k2, same r, the integral over when one d3r gives you a delta function in the k's, and then it is k and minus k. So that's what we did. And now you can see that if that there is no reason for me to have the grad phi square separately, because all that, if I had a grad phi over here, then all that it would do is give me a k square over here. So if this was grad phi square d3r, then it would simply go to k square phi k phi minus k d3k over 2 pi. So that, because the gradient, you write this as phi k e to the power I k dot r, the gradient brings down a I k, the other gradient brings down a minus I k, so that's the k square over here. So that's that. So that is why I didn't bother. You get the answer with A and then replace A by A plus k squared. So that's that. All right. So this was the Fourier transform.
Sir,
Yes.
so in the expression of f of phi, why we did not consider odd powers of phi?
Odd powers. Because I'm assuming the up-down invariance. So this is, it has isotropic. I'm starting out with a system which has no preference in direction, and it does not care about up-down. It does not care about the angle. Therefore, it is all even powers, and if this was a question of a vector, then it would be all scalar quantities over here. That is, if I go to a phi vector, then the phi square would be phi 1 squared up to phi n squared. This is you start with a situation which is perfectly symmetric, and that's the way life is. I mean, if you are going to talk about energy of a magnetic system where there is no external magnetic field, the answer is that the energy is m squared. So that's the way things go if nothing special is happening. So there is no reason to say that plus m, whether the magnetization is pointing up or whether it is pointing down, makes no difference if I don't have a magnetic field. If I have a magnetic field, then the symmetry is broken, and I have to put in an external, because I would be putting in a term which is minus h dot phi. But if no external field, up, spin down makes no difference. That is why it is just phi squared. Similarly, it does not matter in which direction the sphere magnetization is pointing, and therefore, I mean, if it is a vector, then it would be phi squared once again under that. So rotational invariance, up-down invariance. So that is what you have in the absence of any kind of biasing, and that's why. So all right, so that is the and now then this meaning of this, as we saw last time, is that you have a whole lot of k's, and this is d phi k. It is pi over k. That is, this can be broken down into phi k1, phi k2, phi m, and so on. And with the phi's in general, I mean, if it is phi k is complex, so you would have all the minuses as well. So it is d phi k, d phi minus k, and similarly. So there is, all right. So that's that's what one is. And now you have to do this in integral over here, and the integral is trivial, because everything is split out. It is e to the power minus a over 2 phi k phi minus k. And then, I mean, for a given k, it is this, and another k is the similar factor over here, similar factor over here, similar factor over here. So what you are seeing over here is pi over pi of k and e to the power minus. So this integral and has become phi k phi minus k d3k, and I can write it as a sum over all the way, and for a specific k it is minus a by 2 phi k phi minus k, and then there are all the k's that you have which are forming a string over there. So it's a pi over here, this factor multiplied for a given k multiplied by a similar factor for another k, and so on. And then for this particular k that we are considering, you have to do an integral which is over d phi k d phi minus k. So you are looking at this phi k phi minus k, and then this is d phi k phi minus k. You can split it up into the real and imaginary parts, and each of them would give you, so phi k is complex, and you can split this up into the write it in terms of the real and imaginary parts, and each one of them is going to be like a by 2 and some let's say this is phi k star, so it is you write phi k as this a plus real plus imaginary, so you have some square over here, and then you have some d phi k over here, and therefore this is going from minus infinity to plus infinity, and the answer is square root of pi. So this is the square root of pi, and then it is a square root of pi over a. So that's the a coming from here. So square root of pi over a, I hope the factor of 2 over here ensures that there is no factor coming from here. So that you can check, it is just a Gaussian integral dx e to the power minus a x square over 2 going from minus infinity to plus infinity. So that's my gamma function. So it is I might have a, so it is a over 2 square root, so square root of 2 over a. So I have to have a square root of 2 over a, and then it is minus infinity to plus infinity, and then it is dy e to the power minus y squared. So that's my gamma function of half. So that's your square root of pi. So it is square root of square root of 2 pi divided by a. All right. So square root of 2 pi divided by a, and I have the a, so you have this for all k, and therefore you are going to pick up 1 over a for each one of them. If I have instead, so now if it is quadratic, which is d phi, and then it is e to the power minus a over 2 phi square plus half grad phi square, that integrated over d3r. Then this part over here is e to the power minus a over 2 plus k square over 2 phi k phi minus k, and summed over all k, summed over, so that it is a pi for all of them. It is like the single factor which we did over here, except that now it is the a is a plus k square. So you are going to get the same answer over here as you got over there, except the a has become a over k square. So it is going to become square root of 2 pi divided by a plus k square. And that's that. That is it. I mean, this is the only thing which can be done. I mean, done exactly. The Gaussian integral. And if I do the Gaussian integral, then the answer is that this integral so this z, which is equal to this, in the Gaussian case, which means that lambda is equal to 0. So this Ginzburg-Landau model, so this is GL and goes to Gaussian if lambda is equal to 0. So the Ginzburg-Landau model becomes a Gaussian model if lambda is equal to 0, and then it is simply the functional integral of e to the power minus a over 2 phi square plus half grad phi square d3r, and the answer is pi over all k's, or that is square root of 2 pi over a plus k square. So it's a product over all possible values. It's an infinite product of this 2 pi square root of 2 pi over a plus k square, where a is this coefficient of the quadratic term over here. So that's the maths that one needs to know. One would obviously have to talk about a little more, but those would be secondary. I mean, it is just that, for example, in the single variable business, which we know that so very well, that if I know integral minus infinity to plus infinity e to the power minus ax squared dx is equal to, which will be 2 over a. If I know this, then it is trivial to find x squared e to the power minus ax squared, because I can get it by taking a derivative with respect to a and a minus sign. So if I know, and then if I want another, I can just take another derivative, and all the moments are going to follow. So that's a very important statement, because later when we are going to do perturbation theory, say that obviously nothing can be done exactly when this is around. So we'll say lambda is small and do a perturbation theory, and then you would be into calculating moments. That is phi squared multiplied by e to the power minus this. So that is like calculating moments over here, and moments are obtained by taking derivatives. So all that I need to know is just one answer. One answer does it all for me, and this is the Gaussian limit, which is this over here. So this is vital. I mean, this particular answer, I mean, this is the, and the fact that all the moments can be obtained by taking derivatives with respect to A is what should be sort of, I mean, ingrained in your mind, that this is something which we would always be able to use. So that's the technology. When it comes to doing the continuous system, this is the technology that one makes use of all the time, and this is where this is how you do it. All right. So I do hope that, I mean, it's clear that what the technology is, because I mean, this is what is really important. So that's the business that we. So now let's talk about that and go back to where we started with, and let's see what the point was. We started with a calculation. What we had to calculate was this functional integral, which is e to the power minus some integral ddx of some function of phi. Now, we'll use the magnetic language and use the language that is, I'll call the phi magnetization, but it is something which can equally well be a density difference or superfluid density if it is a superfluid transition, superfluid density fluctuate. But anyway, I mean, the generic name is, let's say, magnetization. And let's suppose that I have this Z, which is, this is what we learned to calculate. And now I'm going to switch on external field. Switch on an external field H, and therefore that will bring on an additional term over here, which is integral. So the contribution to the energy would be, it is phi, so we'll just disregard a vector and so on. The contribution to the energy is minus h phi dx. H we will take to be uniform, so I'll take the h out over here, and so it is minus h integral phi dx, and therefore I have over here phi dx. It's all in a d-dimensional space, so there should be. So it is coupled. So a small external field. So small external field, the field is small so that only the lowest power of h can be of any relevance. And we are going to, at the end of the story, that we will take the limit of h going to 0. So we will take, and so why, I mean, what's the point of doing that? So the point of doing it is that I want to, what is it that I want to calculate? What I want to calculate is, one, average magnetization, let's say. Two, susceptibility. 3 may be things like specific heat. So what are the physical quantities? What are the physical responses that one wants to calculate? One wants to calculate things like the average magnetization, which should be 0 above and non-zero below, a susceptibility near the transition point, and the things like the specific heat and so on and so forth. So that is what, those are the things that we would like to calculate. So, all right, if that is what one would like to calculate, one would like to ask that how does one go about calculating things? So, for example, if I have to calculate the magnetization, then what is the magnetization? What does, so I have put in this external field over here as the probe of the system. And now I want to know this, what the magnetization that I want to talk about is a spontaneous magnetization, the average magnetization for H going to 0. So that is the spontaneous magnetization. That is what the transition is all about. You are going from a state where the spontaneous magnetization is 0 to a state where, so if this is the spontaneous magnetization M and this is your T, then at this TC over here, so the graph is like this and then goes like this. And it is this region, this is where we are interested, where the magnetization just sets in and starts growing. Now, what is the magnetization? What is the magnetization? The magnetization is obtained. So if I go back to thermodynamics, then the thermodynamic free energy is minus kT log Z. So that is the thermodynamic free energy, not to be confused with this F over here, unfortunate. Let's put a thermodynamics over here. So FTH equal to minus kT log Z. And then if I have a magnetic external magnetic field, then your TDS is going to become T, the internal energy, which is your here is your du, and then there is the work done. The work done, if I change the magnetization, so now it is in terms of the the work done is in terms of the magnetization. So it is minus this MdH over here. So if my M is and I change the magnetic field a little bit, the magnetic energy is your minus MH, and so the work done minus MdH. The signs one would have to be careful, but hopefully we'll get the sign right. So there is, this is the magnetic contribution to the thing over here, to the work done over here. Here is the internal energy, and then there is now the internal energy also has to change. It is going to be there would be a magnetic part in this internal energy over here, which one would have to keep track of. But the free energy, which is this, F is equal to E, which is this or U minus, that is the definition. It is U minus TS. That is the definition of the free energy when you didn't have any magnetization in the system. This is just the thermal energy of the system. And now if it is F, which is the internal energy will be picking up minus mH, and you would be looking at U minus Ts minus mH. So here is the actually, all right, I need to probably make correction also over there, that U would have this part which is U minus MH. The better the signs have to be more importantly correct. It is the work done which is minus MDH, and therefore this is now with the U written as U minus MH. Well, let's work it out and see where some things need to be changed here or there. DF is equal to DU minus TDS minus SDT minus MDH minus HDF. So DF equal to DU minus TDS minus SDT minus this, and it is this DU minus TDS which cancels out this MDH, which is where, I mean, this is why the point is I should have gone with UDS. Just a minute. The definition of this with H, sorry, it's a PDV. P is like the H. It should have been over here the HDM, the analog of the PDV. So that is your minus HDM over here, and DF is equal to DU. So U has a part of it which is U goes to U minus MH. So it is DU minus TDS minus SDT minus MH. TDS cancels the DU minus HDM. So this DU and HDM, they cancel out. It's the SDT, and it is del F del H is at constant T is equal to minus M. So that's the thermodynamic identity that one needs to make use of, that del F del H is equal to minus M at constant T, and therefore it is this F thermodynamics. So the F thermodynamics over here, so it is this part which is minus M, and it is kT log Z, and I have this log Z over here from. So it is log Z which is given by that, and now it is equal to, so del F del H, so this is M over here, so minus M, minus sign taken out, KT, this is Z as a function of H, so it is 1 over Z del H. So M is equal to KT 1 over Z del H. Now here is your Z over here, and therefore now you are going to take a derivative with respect to H, and that derivative is going to bring down this quantity over here. So this is equal to KT divided by Z, and it is del Z del H. So del Z del H brings down that quantity, so it is integral. Now it is integral, there is d phi, and there is going to be this integral phi x ddx, and then there is this weight factor over here. You want the zero field magnetization, therefore M, when H tending to 0, is going over here, you are going to see only this part. So only this part over here. So only that part over there, and the z over here is also in the limit. So this is all in the limit of the, and so what is it that one is looking at? One is looking at 1 over z, and therefore it is this phi of x dx with this thing, and that is the expectation value of the field of the phi x dx. So it is this quantity for what the magnetization is phi of x weighted by this factor e to the power that, and divided out by the integral of that factor, which is just the definition, that is the expectation value of this field phi of x over here. The ddx simply gives you the volume, which makes it the extensive quantity. So this m, which is h tending to 0, h tending to 0, is simply setting everything else as just ignoring the rest of it. Really, at this point, is the average value of the field phi of x. So m of h tending to 0 is the average value of phi of x. That is how. So question is, given this free energy, what in the world do I do with it? I ignore this part, calculate the expectation value of phi. That is going to be the physical magnetization. What is the susceptibility? The susceptibility is, so this is your average magnetization. Now, what is the susceptibility? If I want to do the susceptibility, then I have to do del m del h. So susceptibility chi is going to be del m del h. Now, this is something I'll leave you. I'll tell you what the answer is, motivate the answer, and then let you worry about figuring it out. Del m, which was a one-time derivative over here of z, brings down this phi of x. When it is a question, and phi of x ddx, when it is a question now of del m del h, I have to go here and keep the h over here and do a derivative once again with respect to h. So that is going to bring down, this brought down a phi x ddx. The next one will bring down, the x is a
two-point correlation function.
Yes, right. Yeah,
It's like a two.
Absolutely, the two-point correlation function. So phi x ddx, phi y ddy, so expectation value of that, and therefore the susceptibility, which is the important thing in, is going to be one of the important magnetization is, and the susceptibility, so ddx, ddy, translational invariance, meaning that phi x, phi y is a function of x minus y alone. The volume comes out, and the susceptibility, therefore, it is extensive. The volume comes out over here through that, and has to be, is taken care of by the volume that you are going to get in the somewhere else. I mean, those will those things take care of themselves. What is important is that it is phi x, phi y. The volume which comes out of the center of mass thing would cancel out if when you are interested in the susceptibility per unit volume, which is the thing which is of interest. So phi x, phi y integrated over this x1, x2, if that's an easier thing to write, so that I can write here ddx1. So the thermodynamic susceptibility is the integral over space. There are three factors which I have not written because they are not awfully, they are important when you just want to nail things down perfectly, but all the action for us is going to lie over here. It's the 2-point function, the correlation function phi x1, phi x2, which gives me the susceptibility. So I know how to calculate the magnetization. I know how to, and it is all done, all the expectation values are calculated by just the phi part of it, because this is the zero field susceptibility. The zero field susceptibility. This is the zero field magnetization that we talked about over here. So it is the zero field magnetization, it is the zero field susceptibility. So two of them we know. There is a third one, which is specific heat, which I had written down. One would have to wait a minute or quite a few minutes before you realize how to get hold of that. So, all right. So, I want the, so we have gone someplace at least. I know that there is a spontaneous magnetization, M as H tends to 0. There is a susceptibility, and I know how to calculate these things. I know that this comes out of expectation value of psi, of phi. I know that this comes from a correlation function phi. There is a specific heat which I don't know yet. But comes the first question, I want to do this functional integral. So how are you going, we have learned only one functional integral, d phi e to the power minus a over 2 plus k square over 2 phi k phi minus k is pi over k and 1 over square root of k square plus a. So that's the only thing that we have learned, that this integral d phi e to the power minus is 1 over square root of k squared over a. So that's the only, I'm just suppressing the other constant. So that's all that I know how to do. But I have to actually do this, and I know that f of phi is, the f of phi in reality is a over 2 phi squared plus half z phi squared plus lambda over 4 phi squared. So very good. So what in the, all right. So now let me do a couple of things first. Let me try to give you an idea of why it is first that why did I stop over here? I mean, why? I'm not going to go beyond that. That is, I'm not going to have higher powers of phi square, or I won't have higher powers of grad phi square, even though they will be they can be isotropic and maintaining the parity. But I have ignored them. What can sort of justify my doing that? Well, the justification, which is sort of part of it, is you cannot challenge. and one another part which is a bit is going to be a little heuristic, but it is worth knowing, worth having a feel for what is going on. I want to know why, for example, if I had a term which is that I have thrown away. I mean, what is wrong with, why is this term in my reckoning smaller than those, or del square phi square? What went wrong with that? Well, all right. So my point is, so the arguments go in this fashion. I'm going to find first what are the dimensions of these constants, a, lambda, mu, and if there was a constant over here, let's say nu, what would be this one of the coefficients I can always take to be unity by a rescaling. So a rescaling can set one coefficient, and then relative to that, all the other coefficients work. So conventionally, we just set this to be 1, and we look at the terms which are. All this is because why set this, why get the coefficient of this? Because the whole business is that there is something called a mean field theory, which is, or Landau theory, where it says that, look, let's just replace, so mean field or Landau theory, which says that, look, let me just start with, let me just talk about phi, where the very slowly varying phi, in space, and forget this term over here. Then the free energy is half a m square plus lambda over and phi is replaced, so notational, the mean value of phi is, so replace phi by a mean value, because there was a spatial variation. That spatial variation you have ignored by saying that I have replaced phi by a mean value, which is essentially phi average value, of phi, which is m. So that is the m square over here, and then you have a m4 over here. And if I have a external field, then it is minus. So that would be the answer. Now the point is that if I'm in H equal to 0, so spontaneous magnetization is what I'm after. So spontaneous magnetization, H is necessary to calculate susceptibilities. Without H, no susceptibility. But spontaneous magnetization, H can be set equal to 0. So spontaneous magnetization, H tends to 0. F is equal to A over 2 m square plus lambda over m4. So how do I calculate the magnetization? I just want, what is what value of m? What is going to be, m can have various values. What is it that you are going to observe? What you are going to observe is the value where is the system going to settle? The system is going to settle at the minimum value of the free energy. So where the thermodynamic state where the system settles is del F del M is equal to 0, and therefore it is A plus lambda M square M. So that is where the system is going to settle. That's the value. Lambda is positive definite, because otherwise if this theory would not be defined. So integral would not exist if lambda is negative. So lambda greater than 0 for existence of integral. So it's that you cannot have e to the power x squared plus x4. That integral does not exist. So blows up. So you have to have x4 coefficient negative, however small. So lambda greater than 0. So lambda greater than 0, if A is equal to 0, then the only solution is M equal to 0. So A greater than 0 implies M equal to 0. So A greater than 0, the system has no spontaneous magnetization. So M equal to 0 if A is, but if A is less than 0, if A is less than 0, then you have three possibilities. There is M equal to 0, and then there is M squared is equal to minus A over lambda. If you look at so now which one of them? So then you have to look at the free energy. So free energy, this is what is going to minimize the free energy. If A is positive, the free energy is going to if A is positive, the free energy as a function of, so this is f of M versus M. So, and the free energy looks like this. But if it is A less than 0, then the free energy looks like this. So it's going to settle either here or here. So if A is less than 0, the system will show a finite value of M. It can be either positive or negative. So it will choose, if you try to cool it down, it will choose one of the two states, either plus or this. So as soon as it chooses, the symmetry is broken. The symmetry that you had in this system, the up-down symmetry which we started out with, is broken as soon as A is less than 0. So that is spontaneous symmetry breaking, that it is now the system still, if you look at it, this is H going to 0 limit, it is a symmetric free energy. It has the free energy is still invariant under the transformation M to minus M. But where is the system going to settle? The ground state of the system does not have the symmetry of the free energy. That is what the spontaneous breakdown of symmetry is all about. The ground state does not reflect the symmetry of the Hamiltonian, or in this case, the free energy. So that is the spontaneous breakdown of symmetry. Over here, the symmetry particular being up-down over here. And you have so A greater than 0, the transition point is A equal to 0. Physically, the transition occurs at t equal to Tc, and therefore you write A equal to A0 T minus. So that sets up the Landau theory. The Landau mean field theory says that this A over here is A0 T minus Tc, the free energy that is in presence of a small external field, which determines this system, is the free energy which describes this system is this. If I'm looking at the H equal to 0 state, then that is a spontaneous breakdown of symmetry when you pass from higher than Tc to lower than Tc. So that is where that is the Landau mean field theory. We can, all right, I still have a few minutes, good. So we can get through this. So this is the first thing that you have noted, that this is the m squared is minus a over lambda, and therefore I think the what I'll have to leave for the next day is the dimensions of these, what is small and what's not small. So, all right. So, m square equal to minus a over lambda means that m square is proportional to Tc minus T, and therefore m is proportional to Tc minus T to the power half. So the critical exponent beta is equal to half. So that's point number one. The next is so, all right. I don't think I need this anymore, right? So, so now the susceptibility, zero field susceptibility, that is take del m del h and then so the minimization condition, if I have an external field, small external field, then the minimization condition becomes m plus lambda m cubed minus h equal to 0. So am plus lambda m cubed minus h. So this is the minimization condition in the presence of this. Del m del h. So now if I do del m del h, then del m del h. So I'm taking a derivative with respect to h times a plus 3 lambda m squared minus is equal to 1. So if I take a derivative with respect to h, then this is what I get. This is, and so this is the zero field susceptibility. Chi is equal to 1 divided by so the linear response, linear susceptibility is a plus 3 lambda m squared. So chi is equal to 1 over a plus 3 lambda m squared. If I'm above Tc, so t greater than Tc, m is equal to 0 and chi is equal to 1 over a proportional to t minus Tc to the power minus 1. So the susceptibility, as you come close to the critical point, diverges as t minus Tc to the power minus 1. What if you are below below Tc? So below Tc,
m square will be minus a by lambda, so it will be minus of.
Absolutely. M squared is equal to minus a by lambda, and therefore the chi is equal to 1 over, this is minus mod a, and this is the A is now negative, and so this is equal to mod A by lambda and plus 3 mod A, which is equal to 1 over 2 mod A. So once again, chi is proportional to Tc minus T to the power minus 1 as you approach the lambda point, the critical point. So it is Tc minus T to the power minus 1, but it was 1 over A over here, and it is 1 over 2A over here. There is, if you recall, that is exactly what we got when we did the did this in the Ising case. So when we did the Ising model and compared the susceptibilities above and below, there was a ratio of ratio of 2. And once again, over here in this Landau-Ginzburg model, you see that in the mean field theory, you have so mean field Ising model gave you the ratio as 2, and so exactly the answers which you got from the mean field Ising also follow from the mean field theory of Landau. So this is now you can also pick up if you are at the critical point. If you are at Tc, A equal to 0, so m is proportional to h to the power 1 over 3. So the definition of the exponent delta was that m proportional to h to the power 1 over delta at t equal to Tc. So if I have a without h, m is equal to 0, but if you have a finite small h, then at Tc, the magnetization is proportional to this, and delta is equal to 3. So I have got my beta, I have got my gamma, and I have got a delta. I don't have alpha. So alpha is which is the critical, which is the specific heat exponent. So the specific heat, I don't have a mechanism at this point to talk about the specific heat. But I have laid the foundation for talking about the specific heat by giving you this information that in this Ginzburg-Landau free energy that we will be using, A is equal to A0 T minus Tc. So this is a decent point to end, that here is the discussion. What we have just gone through tells me that I have done the mean field theory for this continuous model. The answer is the same as the mean field theory for the Ising model, but it has also given me some insight into this functional, that this term A, if this functional is going to describe a transition, then a second order phase transition, then this A0, A has to be some constant A0 times T minus Tc. So this f of phi is going to be the starting point, and for some reason this term and all terms of this kind are not going to be so important. And there is what we'll start out next time is with a heuristic argument by why these can be ignored, or when can they be, more importantly, when can they be ignored, and so on. So we'll start with that next time, that why we are happy to drop all terms which are higher order than what we have up to this point. So So that's important to know before we go any further. So that is where we will start out. But for now, what has happened is that we have finished the mean field theory. We have done mean field for the Ising model. We have done mean field for this continuum model. They give me the same kind of answer. And except that you will see that this way of doing it through the continuum over here allows me an access to the specific heat also. So we'll and in addition we have learned another word, that there is something called a Gaussian model, and the Gaussian model is determined by f phi equal to a over 2 phi square plus half grad phi square, and is defined only for t greater than equal to tc. So if t is less than tc, then this Gaussian model is no longer going to be, because there would be some situations where this exponential e to the this is going to become negative, and you will have e to the power positive things, and making the functional integral ill-defined. So Gaussian model is this one model over here, where f phi is this, and it's defined only for t. So all right, so we have gone somewhere. And next time we'll start talking about what the various features of this are. And after we have done that, we'll then go back to discrete models for a while, because we need to talk about one-dimensional, the solutions of the Ising models go beyond the mean field theory. So we need to look at the discrete models and what their solutions look like, then come back and talk about what it looks like over here. So that is going to be the agenda. Next class is certainly, we want to talk about, to a certain extent, the Gaussian model and the question of, so then we'll go after that to the Ising model once again. And this time with the whole, not a mean field theory. All right, so that's where we are. And so once again, the point is that if there can be queries, the best thing is that best way of handling it is, if you have any, just write to me, and I'll send you answers. If you are on campus, any the PhD students, if there are any PhD and you happen to be, then you can come and talk to me. Others certainly can communicate whatever you want clarification on. You can send a question and I'll certainly respond. All right. So next week then